Our cosmic story begins in the cold, dark expanse of space, within a nebula, a vast cloud of gas and dust. These nebulae, often remnants of past stellar explosions, are the nurseries of stars, the cosmic wombs where gravity gathers and compresses these interstellar ingredients. Imagine a slow, graceful dance as particles drawn together by their mutual gravitational attraction begin to clump together. Over eons, these clumps grow larger, pulling in more and more material, their cores becoming denser and hotter. This is the first act in the drama of a star's life, the slow and steady accumulation of matter, the build-up to a brilliant debut. As the core of this collapsing cloud heats up, a protostar is born, a stellar embryo radiating heat and light, its future still uncertain. Will it gather enough mass to ignite the nuclear furnace at its core and achieve starhood? Or will it remain a stellar infant, forever on the verge of brilliance, but never quite reaching its full potential? The answer to this question lies in the delicate balance between gravity, relentlessly trying to compress the protostar, and the outward pressure generated by the heat of its core. This stage is set for the next act in our cosmic drama, the main sequence where a star truly shines. But that, my friends, is a story for another time. In the vast, cold expanse of a nebula, gravity reigns supreme. It's a force that acts across unimaginable distances, pulling together particles of dust and gas like a cosmic sculptor shaping a masterpiece. These particles, remnants of long-dead stars, are the raw materials for new stars waiting for the celestial choreography to begin. Imagine a slow waltz, a delicate dance of attraction as gravity draws these particles closer. At first, the movements are imperceptible, a subtle shift in the cosmic ballet. But as more particles gather, their combined gravitational pull strengthens, drawing in even more material from the surrounding nebula. This process, known as gravitational collapse, is the engine that drives the birth of stars. It's a relentless force, squeezing the cloud of gas and dust, causing it to spin and flatten into a swirling disk. As the collapse continues, the core of this disk becomes denser, hotter, a crucible where stellar alchemy is about to begin. Think of a figure skater pulling their arms in during a spin, their rotation accelerating as their mass becomes more concentrated. Similarly, the collapsing cloud of gas and dust spins faster and faster as it shrinks, transforming from a chaotic cloud into a more organized, rotating structure, a cosmic dance floor for the birth of a star. As the nebula's core continues to collapse under gravity's relentless pull, it transforms from a cold, diffuse cloud into a hot, dense sphere. The particles, once drifting effortlessly through the void, now collide with increasing frequency and ferocity, generating heat and light. Imagine a cosmic mosh pit, particles jostling and colliding, their energy transforming into heat and light. The temperature at the core steadily rises, a slow burn that will eventually ignite the stellar furnace. This heat, however, also creates an outward pressure, a force that resists gravity's relentless squeeze. This delicate balance between gravity's inward pull and the outward pressure from the hot core is crucial. It's a cosmic tug-of-war that determines the fate of a star. If gravity wins, the collapse continues unchecked, potentially leading to the formation of a black hole. But for a star to be born, a different fate awaits. The intense heat at the core must trigger a new process, a process that will release unimaginable amounts of energy, pushing back against gravity and igniting the star's long-lasting fire nuclear fusion. The core of the collapsing cloud, now a swirling inferno of heat and pressure, reaches a critical temperature, a scorching 10 million degrees Celsius. This is the ignition point, the moment when hydrogen atoms, the simplest and most abundant element in the universe, are forced together with such violence that they fuse, creating helium and releasing a tremendous amount of energy. This process, known as nuclear fusion, is the heart of a star. its lifeblood. It's the engine that powers the sun and every other star in the universe, a cosmic furnace where lighter elements are transformed into heavier ones, releasing energy in the process. The energy released by fusion travels outward from the core, pushing against the inward pull of gravity. This outward pressure creates a delicate balance, a state of hydrostatic equilibrium, where the star neither collapses further nor expands outward. It's a stable state, a long-lasting equilibrium that allows a star to shine brightly for millions, even billions of years. This is the moment a star is truly born, the moment it emerges from the dusty cocoon of its nebula and takes its place in the cosmic tapestry. No longer a collapsing cloud of gas and dust, it's now a celestial beacon, a self-luminous sphere of plasma, radiating energy across the vastness of space. The newborn star, however, is not yet fully formed. It's still surrounded by a swirling disk of leftover gas and dust, remnants of its chaotic birth. This disk, known as a protoplanetary disk, is where planets may eventually form, but that's a story for another time. The star, now a protostar, continues to gather material from this disk, its gravity pulling in gas and dust, further increasing its mass and energy output. It's a time of growth and change, a period of adjustment as the protostar settles into its new life. As the protostar evolves, it goes through various stages of instability, marked by fluctuations in brightness and outbursts of energy. These are the growing pains of a young star, a sign that the delicate balance between gravity and fusion is still being fine-tuned. Eventually, after millions of years, the protostar will gather enough mass and achieve a stable state of nuclear fusion in its core. It will then shed its dusty cocoon, blowing away the remaining gas and dust in its protoplanetary disk, and emerge as a fully fledged star ready to take its place on the main sequence, the longest and most stable stage of a star's life. But that, as they say, is a story for another time. Our stellar story now shifts to the main sequence, a stage that marks a star's adulthood, its prime time. Imagine a vast cosmic dance floor filled with stars of all sizes and colors, each radiating energy generated by the nuclear fusion in their cores. This is the main sequence, a period of stability and equilibrium where stars spend the majority of their lives. Think of a well-tuned engine humming along steadily, converting fuel into energy. That's a star on the main sequence, its core a nuclear furnace fusing hydrogen into helium, releasing a constant stream of energy that travels outward, counteracting the inward pull of gravity. This balance, this cosmic equilibrium, is what defines the main sequence. It's a period of relative calm where a star shines brightly, its size and luminosity remaining relatively constant for millions, even billions of years. But like all good things, the stability doesn't last forever. The hydrogen fuel at a star's core is finite, and eventually this fuel will begin to run out, setting the stage for the next act in our cosmic drama. Section 2, the Cosmic Balancing Act, Hydrostatic Equilibrium. To truly appreciate the main sequence, we need to delve deeper into the forces at play within a star. It's a constant battle between gravity relentlessly trying to crush the star inward and the outward pressure generated by nuclear fusion in the core. Imagine a balloon, its rubber skin stretched taut by the air pressure inside. Similarly, a star is held together by a delicate balance of forces. Gravity pulls all the star's matter towards its center, while the outward pressure from the core pushes back, preventing a catastrophic collapse. This state of balance, known as hydrostatic equilibrium, is what keeps a star stable and shining. It's a remarkable feat, a cosmic tightrope walk that can last for billions of years. This equilibrium, however, is not static. It's a dynamic process, constantly adjusting to slight variations in energy production and gravitational forces. As hydrogen is consumed in the core, the energy output can fluctuate, causing subtle expansions and contractions of the star. Section 3. Stellar diversity on the main sequence. Not all stars on the main sequence are created equal. They come in a variety of sizes, masses, and colors, each with its own unique story to tell. The most massive stars, the blue giants, are like cosmic rock stars, living fast and dying young. They burn through their hydrogen fuel at an incredible rate, shining brilliantly for a few million years before meeting their explosive end. On the other end of the spectrum are the red dwarfs, the smallest and coolest stars on the main sequence. These stars are incredibly fuel efficient, sipping on their hydrogen reserves and shining dimly for trillions of years. Our Sun, a yellow dwarf, falls somewhere in between these extremes. It's a middle-aged star, about halfway through its 10 billion-year lifespan on the main sequence. It's a comfortable, stable star, providing just the right amount of heat and light to support life on Earth. The diversity of stars on the main sequence is a testament to the vastness and wonder of the cosmos. It's a reminder that our universe is filled with an incredible array of celestial objects, each with its own unique story to tell. Section 4. A glimpse into the Sun's future, our star's destiny. As we gaze upon the Sun, our own life-giving star, it's natural to wonder about its fate. What will become of our Sun, and how will its evolution affect Earth and its inhabitants? In about 5 billion years, our Sun will begin to exhaust the hydrogen fuel in its core. This will mark the end of its main sequence life, and it will begin to evolve into a red giant. As it expands, its outer layers will engulf the inner planets, including Earth. This is a sobering thought, a reminder of the impermanence of even the most seemingly constant objects in the universe. But even in its death throes, the Sun will play a crucial role in the cosmic cycle of life and death. Its outer layers, enriched with heavy elements forged in its core, will be expelled into space, seeding the interstellar medium with the building blocks for new stars and planets. But that, as they say, is a story for another time. We've witnessed the Sun in its prime, a radiant beacon steadily fusing hydrogen into helium, its energy a life-giving force across our solar system. But even stars experience the passage of time. Deep within the solar core, a drama is about to unfold, a story of dwindling resources and impending transformation. Imagine a campfire, logs crackling merrily, providing warmth and light. But as the night wears on, the flames begin to die down. The wood slowly consumed, leaving behind embers and ash. Similarly, our Sun's hydrogen fuel, its source of life-giving energy, is not infinite. Over billions of years, the core slowly transforms, hydrogen exhausted, replaced by an ever-growing core of inert helium ash. This helium core, unable to sustain the same level of nuclear fusion as hydrogen, begins to contract under its own gravity. This contraction generates heat, intense heat that radiates outward, pushing against the inner layers of the Sun, causing them to expand outward. Our Sun is about to enter a new phase, a dramatic transformation that will alter its appearance and its fate. This impending helium crisis, as astronomers call it, is not a sudden event. It unfolds over millions of years, a slow, inexorable shift in the balance of power within the Sun's core. The stage is set for a dramatic expansion, a transformation from a yellow dwarf into a red giant, a stellar metamorphosis of epic proportions. As the helium core contracts, temperatures soar, driving a wave of energy outward. The Sun's outer layers, responding to this intense heat, begin to expand like a balloon inflating, growing larger and larger. Our once familiar yellow sun transforms into a colossal red giant, its surface cooling as it expands, its color shifting to a deep, ominous red. Imagine a vast glowing orb, hundreds of times larger than the sun we know, engulfing the orbits of Mercury and Venus. Earth, if it survives this expansion, will be a scorched, barren wasteland, its oceans boiled away, its surface a molten sea. But even as the red giant phase spells doom for the inner planets, it's a time of intense stellar activity, a period of both creation and destruction. The core, now a superheated furnace, reaches temperatures high enough to ignite helium fusion, converting helium into carbon and oxygen. This helium burning releases even more energy, briefly prolonging the star's life. The red giant phase is a time of instability, marked by pulsations, stellar winds, and the ejection of vast shells of gas and dust into space. These stellar winds, like cosmic breaths, carry away a significant portion of the star's mass, enriching the interstellar medium with the building blocks for future generations of stars and planets. Deep within the heart of the red giant, a cosmic alchemy is at work. As the helium fuel is consumed, the core contracts further, temperatures and pressures escalating to unimaginable levels. This extreme environment allows for the fusion of heavier elements, a process known as stellar nucleosynthesis. Imagine a cosmic forge where the intense heat and pressure act as a cosmic hammer, fusing atomic nuclei together, creating heavier and heavier elements. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and so on, building up the elements of the periodic table, one fusion reaction at a time. This process continues, forging elements as heavy as iron, each step releasing energy but requiring ever-increasing temperatures and pressures. Iron, however, marks a turning point. Fusing iron requires more energy than it releases, and the star's core, now a dense ball of iron ash, can no longer support itself against the relentless crush of gravity. The stage is set for a cataclysmic finale, a stellar explosion of unimaginable power, a supernova that will mark the end of one star's life and the birth of something new and wondrous from its ashes. Deep within the heart of the red giant, the once mighty furnace of creation faces its ultimate challenge. The core, now a dense sphere of iron, can no longer sustain the relentless crush of gravity. The fusion reactions that kept the star shining for billions of years grind to a halt. Iron, the star's final alchemical creation, becomes its undoing. Imagine a mighty dam holding back a raging torrent of water. For eons the dam has held, but the pressure behind it continues to build. Finally, the dam can withstand no more and a catastrophic breach occurs. Similarly, the outward pressure generated by nuclear fusion, the force that has held gravity at bay for so long, can no longer counter the overwhelming weight of the iron core. This is the iron crisis, the point of no return for a massive star. The core, once a source of life-giving energy, becomes a ticking time bomb, a harbinger of cosmic doom. With no more fuel to burn, no more energy to counter gravity's relentless pull, the core collapses in on itself, a catastrophic implosion that unfolds in a fraction of a second. As the core collapses, it reaches unimaginable densities, billions of times denser than the densest materials on Earth. Protons and electrons are crushed together, forming neutrons, releasing a torrent of neutrinos, ghostly particles that stream out into space at nearly the speed of light. This neutron core, a dense ball of nuclear matter, becomes the star's last stand against oblivion. The implosion of the core releases a shock wave, a wall of unimaginable energy that propagates outward through the star's layers. This shock wave, traveling at nearly the speed of light, slams into the infalling outer layers, compressing and heating them to billions of degrees. This intense heat ignites runaway nuclear reactions, fusing elements heavier than iron, elements like gold, platinum, and uranium. Imagine a cosmic fireworks display, a billion suns exploding in unison, a blinding flash of light and energy that illuminates the galaxy. This is a supernova, the explosive death throes of a massive star, an event of unparalleled violence and beauty. The supernova blasts the star's outer layers into space, a cosmic tempest of gas and dust, enriched with heavy elements forged in the heart of the explosion. This expanding cloud of debris, known as a supernova remnant, will seed the interstellar medium with the building blocks for new stars and planets. Supernovae are not merely destructive events, they are also engines of cosmic creation, recycling the elements of life and death throughout the universe. The iron in our blood, the calcium in our bones, the gold in our jewelry, all were forged in the fiery crucible of a supernova, scattered across the cosmos only to coalesce again, forming new stars, planets, and ultimately life itself. As the supernova fades, leaving behind a ghostly echo of light and expanding debris, we are left to contemplate the remnants of the star's core. The fate of this core, the heart of the once mighty star, depends on its mass. If the core is less than about 1.4 times the mass of our Sun, it will become a neutron star, an incredibly dense sphere of neutrons, a cosmic nucleus just a few miles across. These neutron stars, spinning rapidly and emitting beams of radiation, are the pulsars, cosmic lighthouses that sweep across the galaxy. If the core is more massive, even the incredible resistance of neutron matter cannot withstand the pull of gravity. The core collapses further, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. These black holes, shrouded in mystery, are the ultimate cosmic abysses, warping the fabric of space-time itself. The remnants of the star's life, whether a neutron star or a black hole, are a testament to the incredible power of gravity, the force that shapes the universe on the grandest of scales. These objects, once hidden within the heart of the star, now stand as cosmic lighthouses, guiding our understanding of the universe and our place within it. And so, our journey through the life cycle of a star comes to an end. A journey that began in the swirling chaos of a nebula and culminated in the explosive death throes of a supernova. We've witnessed the birth of stars, their long and steady lives on the main sequence, their dramatic transformations into red giants, and their ultimate demise, leaving behind remnants both wondrous and enigmatic. But this is not the end of the story. The death of a star is not an ending, but a beginning. The material blasted into space by a supernova, enriched with the heavy elements forged in the star's core, will eventually coalesce again, forming new stars and planetary systems. This cosmic cycle of life and death, of creation and destruction, is a fundamental principle of the universe. It's a cycle that has been playing out for billions of years, from the first generation of stars to the stars we see shining in the night sky today. The atoms in our bodies, the air we breathe, the very ground we stand on, all were once part of a star, forged in the heart of a supernova and scattered across the cosmos. We are, quite literally, star stuff, connected to the universe in a profound and intimate way. As we ponder the vastness of space and the immensity of time, it's easy to feel small and insignificant. But the story of a star's life cycle reminds us that we are part of something much grander than ourselves, a cosmic tapestry woven from the remnants of stars long gone. The next time you gaze up at the night sky, take a moment to appreciate the countless stars that shine down on us. Each one of those points of light represents a story, a journey through the cosmos filled with drama, transformation, and ultimately renewal. The stars are not just distant objects in the sky, they are our ancestors, our creators, and our connection to the universe as a whole. Their stories are our stories. Their atoms are our atoms. Their fate is intertwined with our own. So let us continue to explore, to question, and to marvel at the wonders of the cosmos. For in the stars we find not only our past but also our future, a future filled with endless possibilities and the promise of new discoveries.